Right now, sunlight is warming your skin, and it comes from the most reluctant reaction in nature. In the core of the sun, the average proton waits billions of years before it fuses with another. That reluctance is the only reason the sun burns steadily for 10 billion years instead of flaring out at once, and the only reason it has lasted long enough for you to be here. By the end of this video, you will understand why the whole universe runs this slowly, not out of patience, but because every process in the cosmos keeps time on a clock set by physics, and we have spent a century learning to read them. Begin with the sun, because it is the clock we live beside. At the center of it, the temperature is about 15 million degrees, and the pressure is greater than anything that exists naturally anywhere on Earth. Hydrogen, there is not a gas in any familiar sense. It is a crush of bare protons and loose electrons, stripped of every structure, moving at hundreds of kilometers a second. You might expect that in a furnace like this, fusion would be instant and total, every proton slamming into its neighbors and releasing energy in one overwhelming flash. The strange truth is the opposite. For any single proton in that core, fusion is one of the rarest things that will ever happen to it. The reason is a chain of obstacles, each one slowing the fire. The first is simple repulsion. Protons carry positive charge, and like charges push each other away, harder and harder the closer they come. Even at 15 million degrees, two protons racing toward one another almost always veer apart before they touch. By the rules of everyday physics, they should never meet at all, because they simply do not carry enough speed to climb the hill of their own repulsion. What lets them meet is a quieter feature of the quantum world. A proton is not only a particle sitting at a point, it is also a wave of probability, smeared faintly across space, and now and then that smear allows it to appear on the far side of a barrier it could never have crossed head-on. Physicists call this tunneling. It is faint and improbable, and only a tiny fraction of collisions ever benefit from it. But in a body the size of the sun, with more protons in its core than there are grains of sand on every shore of the Earth many times over, even the rarest event happens often enough to matter. Tunneling, though, is only the gatekeeper. Beyond it lies a far deeper bottleneck, and this is the one that truly sets the sun's pace. When two protons do finally touch, they almost always spring apart again at once, because two protons cannot bind together as they are. To make the first stable building block, one of those protons has to change its very identity in the same fleeting instant, turning into a neutron, so that the pair can hold together as a single nucleus. That transformation is governed by the weak nuclear force, the faintest of the forces that shape matter, and it is so reluctant to act that the overwhelming majority of proton pairs come and go without it ever happening. A proton may collide, tunnel, and touch countless times over the age of the solar system and still not fuse. On average, a given proton in the sun's core waits something on the order of billions of years for its turn. The fire of the sun is throttled not by a shortage of fuel or heat, but by the sheer unwillingness of the weak force to act. This is why a star is steady rather than explosive. If the first step of fusion were easy, a body like the sun would release its energy in a single moment and tear itself apart. Instead, the reaction is held to a crawl, and that crawl is what makes a star a place rather than an event. Consider what it actually produces. Watt for watt, a given volume at the center of the sun gives off less heat than the same volume of a compost heap quietly rotting in a garden. The core is not a roaring blaze. It is a vast, faintly warm thing. The sun blazes across the sky only because it is enormous, stacking that gentle output through a volume more than 1,000,000 times the size of the Earth. Slowness, scaled up to the size of a star, becomes a light that can warm a planet for 10 billion years. If you find these reflective explorations of the cosmos meaningful, a like or a subscribe helps us continue making them. That figure, 10 billion years, is the one that matters, and it is no accident. The weakness of the weak force, the difficulty of tunneling, the precise temperature of the core, together these fix how long the sun can shine, and the answer is not the millions of years you might guess from a fire, but thousands of millions. Roughly 4.5 billion of them have already passed since the sun first ignited from a collapsing cloud. Another 5 billion or so remain before the hydrogen at its heart begins to run low. We exist in the long, quiet middle of that span, warmed by a reaction so slow that it has barely registered our entire history going by beneath it. To convert as much hydrogen as the sun does each second, some 600 million tons of it, sounds like violence, yet spread across a body that vast it is the gentlest possible simmer, A fire that loses track of millions of years, the way we lose track of a single afternoon. Hold on to that idea of a fixed span, because it is the thread that runs through everything that follows. The sun does not burn for 10 billion years by chance, and it does not burn for 10 billion years out of some patient temperament. It burns for 10 billion years because a particular set of physical laws, the strength of electric repulsion, the rules of the quantum world, the feebleness of the weak force, fixes the rate at which it can consume its fuel. Change any one of those laws, even slightly, and the number would change with it. A stronger weak force, and the sun would burn faster and die young. A weaker one, and it might barely shine at all. The sun keeps time, and the laws of physics are what wind the clock. What is true of the sun turns out to be true of the cosmos at every scale. Nothing we will look at moves quickly, and in each case the slowness has a cause that can be named and, remarkably, measured. A cloud of gas takes millions of years to fall together into a star, and there is a specific reason for that delay, written in the density of the cloud and the pull of gravity. The young universe took hundreds of thousands of years to cool enough to turn clear, and that pause can be set down as a temperature and a rate of expansion. The first stars took hundreds of millions of years to appear. Galaxies take hundreds of millions of years to turn once. Planets gather grain by grain across millions of years, and the rock beneath your feet is folded and remade over hundreds of millions more. Every one of these is a clock, and behind every clock is a mechanism. None of it is in a hurry, and none of it is waiting. Each process simply runs at the rate its physics allows, no faster and no slower. The real story, then, is not that the universe is slow. It is that the universe is precise, and that its precision plays out over spans of time so vast they almost defeat the imagination. The deeper surprise is that we have managed to read these clocks at all. We are creatures whose entire recorded history would fit, many times over, inside a single rounding error of the sun's lifetime. A human heart beats perhaps 3 billion times across 80 years. The sun will shine longer than the whole present age of the earth, several times over, before it so much as changes character. And yet, in little more than a single century, working across the boundaries of physics, astronomy, geology, and biology, people have worked out not only how old these things are, but why each of them takes as long as it does. That is the quiet achievement underneath all of this, that a fast and short-lived species learned to read the slowest timekeepers in existence, and to explain the readings. Much of what follows is that detective story, the measurements, the fierce arguments, the brilliant wrong answers, and the people who eventually got it right. But before any clock can be read, there is a problem so basic that it is easy to overlook entirely. Everything we know about the depths of the cosmos, we know from its light, and that light does not arrive the instant it is sent. It travels at a fixed and final speed, the fastest there is, and even so it takes time, sometimes a little, sometimes almost beyond counting, to cross the distances involved. The very first clock we have to understand is not inside the sun at all. It is the delay written into every beam of light that reaches us. The reason the night sky shows us not the universe as it is, but the universe as it once was. The strangeness of the night sky is that it does not exist. Not as a single picture, anyway. When you look up and take in the scattered lights overhead, you are not seeing a place. You are seeing a heap of separate moments, none of them now, each one carried to you by light that set out at a different time and crossed a different distance to arrive. The universe never lets you see it as it is. It only ever lets you see where it has been. This follows from a single fact, one that took a surprisingly long time to establish. Light does not travel instantly. For most of human history, it was assumed to be infinitely fast, arriving everywhere the moment it was made. A candle lit in a dark room seems to fill it at once. The sun appears the instant the horizon clears. There is nothing in ordinary experience to suggest a delay. The first person to prove otherwise was a Danish astronomer named Ole Rømer, working at the Paris Observatory in the 1670s. He was not trying to measure the speed of light at all. He was studying the moons of Jupiter, and in particular, the innermost of the bright ones, which slips behind the giant planet and out of sight on a clockwork schedule, eclipse after eclipse, as regular as anything in the sky. What Rømer noticed was that the schedule drifted. When the Earth, in its own orbit, was on the near side of the Sun and close to Jupiter, the eclipses ran early. When the Earth had swung around to the far side and was more distant, the same eclipses ran late, by as much as a quarter of an hour. The moon itself could not be speeding up and slowing down to suit the Earth's position. That made no sense. The only thing that changed was the distance the light had to cross to reach him. Rumor understood that the lateness was the light itself running behind, because when Jupiter was farther away, its light had a greater gap to span, and spanning it took measurable time. He had found the first proof that light has a finite speed, and he had read it off the timing of a moon hundreds of millions of kilometers away. It was, in a sense, the first cosmic clock ever decoded. Rumor himself did not turn his discovery into a precise number. He was content to have shown that light took time at all. It fell to others, working from his figures, and from a better grasp of the size of the Earth's orbit, to convert the delay into a speed. And when they did, the answer was so vast that many refused at first to believe it. A thing that crossed the gulf between the sun and the Earth in minutes seemed less like a moving object than like an instant smeared thin. Yet the measurement held, refined again and again over the centuries that followed, until the speed of light became one of the most precisely known quantities in all of science. The speed he had stumbled upon is almost absurdly large by any human measure. Light crosses very nearly 300,000 kilometers in a single second. It could circle the Earth 7.5 times while you finish saying the word. At that pace, within a single room or a single planet, the delay is far too small to notice, which is exactly why it stayed hidden for so long. But the cosmos is not a room. Its distances are so enormous that even the fastest thing in existence is left crawling across them, and the delay stops being a technicality and becomes the dominant fact about everything we see. Start close to home. The light reaching you from the sun is already old by the time it lands. It left the sun's surface about 8 minutes earlier and has been falling outward across the solar system ever since. If the sun were somehow switched off, you would feel its warmth and see its disk for 8 more minutes, entirely unaware that the source was already gone. Step further out, and the delays lengthen sharply. The nearest star beyond the sun lies a little over 4 years away at the speed of light, which means its light shows it to you not as it is tonight, but as it was 4 years ago. There is no way to see it more recently than that. There is no faster signal to check it against. 4 years is simply the closest the universe will let you come to its present. And these are the near neighbors. Look toward the faint band of the Milky Way, and much of the light gathering in your eye set out tens of thousands of years ago, when the most recent ice age still held the planet. The great spiral of Andromeda, the most distant thing most people can see without a telescope, lies about 2.5 million light-years away, and the light arriving from it tonight began its journey 2.5 million years ago, before our own species existed, when the creatures that would eventually become us were still early and few on the plains of Africa. You cannot see Andromeda as it is. No one ever will. By the time its present light reaches any eye, that eye will belong to something living millions of years from now. This is why a single glance at the sky is not one moment, but many. The planet you notice low in the west is minutes old. The bright star beside it is decades old. The cluster behind them is thousands of years old, and the faint smudge past that is millions. They appear to hang together on the same dark sheet, but they are nothing of the kind. They are a stack of different pasts, layered by accident of distance, presented to you as if they were simultaneous. The sky is less like a photograph than like an archive in which every shelf holds a different century, all of them open at once. For a long time, this delay was treated as a nuisance, a barrier between us and the real, current universe we wished we could see. The shift that changed astronomy was the realization that the delay is not a barrier at all. It is a gift, because light from farther away is also older. Looking out into space is the same act as looking back into time. A telescope pointed at a distant object is, quite literally, pointed at the past, and the deeper it sees, the further back it looks. We cannot travel to the early universe, but we do not need to. Its light is still arriving, having spent billions of years on the way, and when we collect it, we are not reconstructing the cosmic past from clues. We are watching it directly, as it happens, on a delay. This turns the whole sky into a record we can read across time, rather than merely across space. Aim deeply enough, and you can see galaxies as they were when the universe was young, still forming, lit by their first generations of stars, because the light they sent out in that distant youth is only now completing its crossing. The deepest exposures ever taken reach objects whose light has traveled for well over 13 billion years, showing them not as they are. They have long since changed beyond recognition, if they survive at all, but as they were when the cosmos itself was a fraction of its present age. There is no other phenomenon in nature that lets us watch the past so directly. To look up is to perform a kind of excavation, where the lowest, oldest layers are not buried beneath us, but scattered across the farthest reaches of the sky. So the very first of the universe's clocks is the simplest one, and it is built into light itself. Distance becomes time, depth becomes history. The finite speed that once seemed a mere limitation turns out to be the instrument that lets us see how the cosmos has unfolded, stage by stage, all the way back toward its beginning. Every other clock we will look at, the slow collapse of gas, the cooling of the early universe, the burning of stars, the building of worlds, we read in light that has spent ages on its way to us, light that shows each process frozen at the moment it was sent. But there is a limit to what this clock alone can tell us. It reveals how things looked at the moment their light departed, and how far away they were. But it does not, by itself, tell us how old they are, or how long they can last. The light from a star shows you the star, not its age. It carries no label saying how many years it has already burned, or how many remain. And in the 19th century, that gap became the center of one of the fiercest arguments in the history of science. Astronomers and geologists and biologists could all see, in their different ways, that the Earth and the Sun were old. What none of them could agree on was how old, and the most brilliant physicist of the age was about to stake his reputation on an answer that was wrong by a factor of more than 200. By the middle of the 19th century, almost everyone who studied the natural world agreed on one thing: the Earth and the Sun were very old. They disagreed, often bitterly, on what very old meant. And the disagreement mattered, because each science needed a different amount of time to make its own story work. Geologists, tracing how slowly rivers cut valleys, and how gradually layers of rock were laid down and worn away, needed hundreds of millions of years at the least. Charles Darwin, building his case that living things had changed shape across countless generations, needed time on a similar scale or greater, because natural selection works only by the accumulation of tiny differences, and tiny differences take an enormous while to add up to a new kind of creature. To the geologists and the naturalists, the past was almost unlimited, a vast, quiet expanse in which slow processes had all the room they needed. Into this came one of the most formidable minds of the age, William Thomson, later ennobled as Lord Kelvin. Thomson was not a man given to loose thinking. He had helped lay the foundations of thermodynamics, had a hand in laying the first telegraph cable across the Atlantic, and brought to every question a rigor that few could match. And when he turned that rigor on the age of the sun and the earth, he arrived at an answer far smaller than the naturalists wanted, and he defended it for the rest of his life. His reasoning began with a fair question: what could possibly keep the sun shining? Whatever the answer, it had to be something that could pour out light at the sun's tremendous rate for the whole of its existence, and the known options were poor. If the sun were simply burning, in the ordinary chemical sense, a great ball of coal set alight, it would consume itself in a few thousand years, and then go dark. That was plainly far too short. The sun had clearly shone over the whole of human history and longer. Chemistry could not power a star. Some deeper source was needed, and the best one available pointed to gravity. Other possibilities had been weighed and found wanting. One popular suggestion held that the sun was fed by a constant rain of meteors and comets falling into it, each impact adding its energy to the fire. Thomson took the idea seriously enough to examine it closely, and showed that to keep the sun burning this way would require so much infalling matter that the planet's own motions would be visibly disturbed by the growing mass at the center of the solar system. No such disturbance was seen. The meteoric hypothesis failed not because it was unthinkable, but because its consequences could be checked and ruled out, which is exactly how a good clock is tested. That left contraction as the strongest candidate standing, and Thomson built his case on it. The idea, first put forward by the German physicist Hermann von Helmholtz and then developed by Thomson, was that the sun shines by slowly shrinking. A body as massive as the sun holds an immense reserve of energy simply in its own gravity, and as it contracts, even very gradually, that gravitational energy is released as heat. A sun that drew its light from its own slow collapse would not need to burn any fuel at all. It would glow from the steady surrender to its own weight. It was an elegant idea, and crucially, it was quantifiable. Thomson could work out how much energy such a process could supply, compare it to how fast the sun radiates, and so calculate how long the supply could last. The answer he reached was a few tens of millions of years, perhaps 20, perhaps a little more, but nothing remotely approaching the hundreds of millions the geologists demanded. He attacked the age of the Earth from a second, independent direction, and to his satisfaction it gave the same kind of figure. The Earth, he reasoned, had begun as a molten body, and had been cooling ever since, its heat leaking steadily out into space. The rate at which heat conducts through rock was something he could measure, and the temperature gradient in mines, the way it grows warmer as you descend, told him how much heat was still flowing out of the planet today. From these he could calculate how long the Earth had been cooling from a molten start to its present state. Again, the answer came back in the tens of millions of years, comfortably less than 100 million, and far short of what the slow grinding of geology seemed to require. Two separate lines of argument, one for the Sun and one for the Earth, both built on sound physics, both pointing at a young world. For the naturalists, this was a catastrophe. Darwin felt it keenly. In the first edition of his great book, he had ventured a rough estimate of his own, that the wearing away of a particular stretch of English countryside must have taken something like 300 million years, and Thomson's limit made such a figure impossible. Under the pressure of the physics, Darwin withdrew the estimate from later editions and confessed, privately, that Thomson's objection was among the gravest his theory faced. Here was the most exact of the sciences, wielded by its most exact practitioner, telling biology and geology that they simply did not have the time they were asking for, and the arithmetic was not wrong. Given everything Thomson assumed, his numbers followed without flaw. That is the part worth pausing on, because it is the heart of the whole matter. Thomson did not make a mistake in his calculations. He made a mistake in his premises, and it was a mistake he could not have known he was making. He had assumed that the only sources of energy available to the Sun and the Earth were the ones 19th century physics knew about: chemical burning, gravitational contraction, the slow leak of primordial heat. He was, in effect, reading a clock, the clock of gravitational collapse, and reading it correctly. The trouble was that it was not the clock that actually governed the Sunday. There was another mechanism at work, hidden inside matter itself, vastly more powerful and vastly slower to exhaust, and because Thomson did not know it existed, he had no way to include it. His timescale was real. It simply was not the Sun's. To his enormous credit, Thomson half saw the gap himself. He stated plainly that his conclusions held only so long as no unknown source of energy was waiting to be discovered, some reservoir not yet imagined by the science of his day. It was an honest caveat, and it turned out to be the exact crack through which the answer would eventually come. He had drawn the boundary of his own knowledge and admitted that the truth might lie beyond it. He simply did not expect that it would. There were even hints, before the decisive discovery, that the premises were shakier than they looked. One of Thomson's own former assistants, the engineer John Perry, pointed out in the 1890s that the cooling calculation for the Earth assumed heat moved through the planet only by slow conduction, as it does through a solid bar. But if the deep interior could stir and circulate, carrying heat upward by the bodily movement of hot material, the Earth could stay warm for far longer than Thomson's model allowed, and his age estimate could be stretched by a large factor. Perry had identified, correctly, that one of the load-bearing assumptions was probably wrong. The lesson was already forming, even if few drew it at the time. A calculation is only ever as good as the mechanism it assumes, and if you have misidentified which process truly sets the pace, you can be rigorous, careful, brilliant, and still wrong by a vast margin. This is the danger that shadows every attempt to read a cosmic clock. The universe does not announce which of its mechanisms is the slow, rate-limiting one. That has to be worked out, and until it is, even an immaculate piece of physics can point confidently in the wrong direction. Thomson's failure was not a failure of skill. It was a failure of inventory, of knowing the full list of forces that nature had at its disposal. And wrong by a vast margin Thomson was. The Sun is not a few tens of millions of years old. It has been shining for some 4.5 billion years, and the Earth formed alongside it at very nearly the same time. Thomson's figure was too small, by a factor of more than 200. The naturalists, with their instinct for almost unlimited time, had been closer to the truth than the most precise physicist of the century. But instinct is not proof, and what geology and biology lacked was a clock of their own, something that could be measured rather than merely demanded, a natural process that ran at a known, unchangeable rate, leaving a record that could be read directly from the rocks and from the Sun's own substance. That clock was about to be found, and it was hiding in the last place anyone in Thomson's generation would have thought to look, not in the heavens, and not in the slow grinding of geology, but inside the atom. In the final years of the 19th century, physicists began to notice that certain elements gave off energy entirely on their own, steadily, with no fire and no chemical change, as though each atom carried a tiny supply that ticked down at its own fixed rate. It was faint, it was strange, and at first no one understood what it meant. But within a few years it would overturn Thomson's verdict completely, supplying both the missing energy source that kept the sun and the earth warm, and, just as importantly, a brand new way to measure how old the ground beneath our feet truly is. The discovery that undid Thomson's verdict began, as so many do, by accident. In 1896, the French physicist Henri Becquerel left some uranium salts resting on a wrapped photographic plate in a drawer, expecting nothing in particular. When he developed the plate, he found it fogged, marked as if by light, though it had sat in complete darkness. Something was streaming out of the uranium on its own, with no spark, no heat, no chemical reaction to drive it. Within a couple of years, Marie and Pierre Curie had taken up the puzzle, given the phenomenon its name, radioactivity, and painstakingly isolated new elements, polonium and radium, that poured out this strange energy far more fiercely than uranium did. A pinch of radium, they found, stayed perceptibly warmer than its surroundings, year after year, releasing heat without any apparent source, and without measurably running down. Here was something genuinely new, matter that gave off energy from inside itself, quietly and continuously, by no process anyone yet understood. The understanding came from Ernest Rutherford and his collaborator Frederick Soddy, working in Canada at the turn of the century. What they realized was startling enough that Rutherford warned Soddy not to say it too loudly, for fear they would be dismissed as alchemists. Radioactivity, they concluded, was transmutation. The atoms of a radioactive element were spontaneously transforming into atoms of a different element, flinging out a fragment of themselves in the process. And the energy Becquerel and the Curies had seen was the energy of that transformation. The old certainty that atoms were eternal and unchangeable was simply wrong. Some kinds of atom were quietly falling apart. But the truly important discovery, for our purposes, was the manner in which they fell apart. Rutherford and Soddy found that each radioactive substance decayed at its own absolutely fixed rate, not a rate that varied with the weather, or the season, or what the substance was chemically combined with, but a constant, built into the kind of atom itself. They captured this in the idea of the half-life, the time it takes for half of any sample of a given radioactive element to decay away. For one substance, that span might be days. For another, thousands of years. For uranium, billions. And crucially, nothing in the ordinary world could touch it. You could heat the material, freeze it, crush it, dissolve it, lock it in rock, or scatter it through the sea, and the half-life would not change by a hair. It was a clock that could not be hurried and could not be slowed, because the decay of each atom was governed not by its circumstances but by the laws of the quantum world, the same deep laws that throttle the fusion in the sunday. There was a further strangeness to it. No one could say when any single atom would decay. One might let go in the next instant, another might wait 1,000,000 years, and there was no way, even in principle, to tell them apart beforehand. The individual event was pure chance. Yet gather a vast number of such atoms together, and that randomness averaged out into something perfectly regular, a rate so steady you could set a calendar by it. Out of countless unpredictable moments emerged one of the most reliable clocks in all of nature, order built, paradoxically, on the back of pure uncertainty. Alpha decay, in fact, turned out to be precisely the same tunneling effect that lets protons creep together in a star, run in reverse, a fragment of the nucleus leaking out through a barrier it should not have been able to cross, at a rate fixed by quantum probability alone. The universe had handed us a timepiece that no force on Earth could tamper with. The implications for Thomson's calculation were immediate and devastating, and the moment they collided is one of the small legends of physics. In 1904, Rutherford rose to lecture on radioactivity and the age of the Earth at the Royal Institution in London, and as he glanced around the room he saw, to his discomfort, the aged Lord Kelvin himself sitting among the audience. Rutherford was about to argue, in effect, that the great man's age for the Earth was badly mistaken. To his relief, Kelvin appeared to be dozing, but as Rutherford reached the decisive point, the old physicist stirred and fixed him with an open eye. Thinking quickly, Rutherford reminded the room that Kelvin had always qualified his result by saying, it held only if no new source of energy were discovered, and that this very evening, that prophetic exception had come true, in the form of radium. Kelvin, the story goes, beamed at him. It was a graceful way to overturn a giant, but overturned he was. Radioactivity supplied exactly the missing source Thomson had left room for, and it broke his argument twice over. It broke the argument about the Earth's age directly. Thomson had assumed the planet was a body cooling steadily from a molten birth, with no fresh heat being added. But the rocks of the Earth contain traces of uranium, thorium, and other radioactive elements, and as these decay, they release heat continuously, deep within the planet, replenishing what leaks away at the surface. The Earth is not merely a cooling ember. It carries its own slow furnace inside it. With an internal heat source, the cooling calculation collapses entirely, and the tens of millions of years it had seemed to demand simply evaporate. The very thing that made the Earth older also explained why it had stayed warm. And it did something even more valuable than removing the old limit. It replaced it with a clock. The clock geology and biology had always lacked. If a radioactive element decays at a perfectly fixed rate, then a rock containing it carries a built-in record of its own age. As the parent element decays, the daughter element it turns into accumulates alongside it, locked in the same crystal. Measure how much of the parent remains and how much of the daughter has gathered, and, because the rate of decay is known and unchangeable, the ratio tells you directly how long the process has been running. It is an hourglass in which the sand falls at a rate fixed by the quantum world, and all you have to do is read the level. For the first time, the age of a stone was not a matter of argument or instinct. It was a measurement. The first to attempt it seriously was an American chemist, Bertram Boltwood, who around 1907 used the slow decay of uranium into lead to date a handful of minerals. His results were rough by later standards, but they were staggering for their day. Some of his rocks came out at hundreds of millions of years, and a few past 2,000 million. At a stroke, the planet was older than Thomson's entire allowance, and the geologist's demand for deep time had been vindicated by the most exact measurement yet made. The work was then taken up and carried for decades by a British geologist, Arthur Holmes, who more than anyone made radiometric dating into a precise science. Holmes published his first book on the age of the Earth while still in his 20s, and spent a lifetime refining the method against fierce resistance from those who distrusted it, slowly building the quantitative timescale of Earth's history that geology uses to this day. The final figure took another half-century to pin down with real confidence, and it came not only from the Earth's own rocks, but from fragments of meteorites, leftover debris from the very formation of the solar system, which had been sitting unaltered in space since the beginning. The Earth's own surface was, in a way, a poor witness to its birth, because the planet endlessly remakes itself. Old rock is buried, melted, and reformed, so the oldest stones we can find are younger than the planet itself. Meteorites had suffered no such renewal. They were pristine offcuts from the moment of assembly, and the clocks inside them had been running, undisturbed, since the solar system first took shape. By measuring the lead isotopes locked inside them, scientists arrived in the 1950s at a number that has held ever since. The Earth, and the solar system with it, is about 4.5 billion years old. Thomson's 20 or 30 million had been wrong by more than 200-fold, exactly as the naturalist's instincts had whispered. The clock inside the atom had settled the longest-running quarrel in the earth sciences, and it had done so with a precision Thomson himself would have admired, even as it demolished his answer. So radioactivity gave us two enormous gifts at once. It gave the Earth an internal source of heat, resolving how the planet could stay warm across billions of years, and it gave us an incorruptible clock for reading the ages of rocks, meteorites, and eventually the solar system as a whole. It seemed, for a moment, as though the same discovery might also solve the original riddle, the one about the Sunday. If atoms held this much hidden energy, perhaps the sun was simply a great mass of radioactive material, decaying away and shining as it went. But that turned out to be wrong. The sun is not powered by radioactive decay. It does not contain nearly enough of the heavy, unstable elements to shine the way it does, and its light comes from something else entirely. Radioactivity had pointed in the right direction, toward the vast reserves of energy locked inside the atom, but it had identified the wrong reaction. Finding the true engine of the sun would take another 30 years, a deeper understanding of the nucleus, and a small group of physicists willing to ask how, exactly, a star turns the lightest element in the universe into light. The energy was nuclear, as radioactivity had hinted. But the sun was not falling apart. It was building up. The answer to the riddle of the sun was suggested, with remarkable boldness, by the British astrophysicist Arthur Eddington in 1920, well before anyone could prove it. Eddington had been thinking about a curious fact uncovered by chemists weighing atoms with new precision. A helium atom, it turned out, weighs very slightly less than the 4 hydrogen atoms that would be needed to build it, lighter by about 7 parts in 1,000. That missing mass was small, but Eddington saw what it might mean. A few years earlier, Einstein had shown that mass and energy are 2 forms of the same thing, bound together by the speed of light squared, so that even a trace of vanished mass corresponds to an enormous release of energy. If the sun were somehow fusing hydrogen into helium deep in its core, then with every helium atom built, that sliver of lost mass would be converted into heat and light. Eddington proposed that this, and nothing else, was the engine of the stars. The numbers were on his side, even if the mechanism was not yet clear. The sun radiates energy at a colossal rate, and Eddington could show that converting hydrogen to helium, with its 7 parts in 1,000 loss of mass, would release enough energy to keep the sun shining not for tens of millions of years, as gravitational contraction allowed, but for many thousands of millions, comfortably more than the geologists and the radiometric daters were now demanding for the age of the Earth. Here, at last, was a power source generous enough to match the deep time the rocks had revealed. Eddington even foresaw a further consequence, that the stars were, in effect, factories slowly transmuting one element into another, and that the helium and heavier matter of the universe might be the accumulated ash of stellar fires. He was reaching, decades ahead of the evidence, toward the idea that the stuff of worlds is forged in stars. It was an astonishing leap, and it ran straight into a serious objection. By the physics of the day, the center of the sun, at 15 million degrees, was nowhere near hot enough to make hydrogen fuse. Protons repel one another fiercely, and at that temperature they should not be moving fast enough to overcome the repulsion and touch. Eddington's critics pointed this out, insisting the sun's interior would have to be far hotter than it could possibly be. Eddington, undaunted, gave one of the more famous retorts in the history of science. The energy of the stars came from this subatomic source, he maintained, and if his colleagues did not believe the sun was hot enough for it, they were welcome to go and find a hotter place. He was certain the answer lay in the nucleus, even if he could not yet say how the reaction managed to proceed. The how arrived from the new quantum physics, and it was the very same effect we have already met twice over. In the late 1920s, physicists realized that a proton approaching the barrier of another's repulsion did not have to climb all the way over it. By the smeared, probabilistic nature of the quantum world, it could tunnel through, appearing on the far side without ever having had enough energy to surmount the wall. Tunneling meant that fusion could occur at 15 million degrees after all, not for most protons, but for a rare lucky few, which was exactly enough. The same trick that lets a fragment leak out of a radioactive nucleus, run the other way, lets 2 protons in the sun creep close enough to join. Eddington had been right to send his critics looking for a hotter place. The place they should have looked was not hotter at all, but quantum. The full accounting was finally worked out at the end of the 1930s, above all by the German-American physicist Hans Bethe, who set down in detail the precise chains of nuclear reactions by which stars turn hydrogen into helium. He showed that in a star like the Sun, the dominant path is a sequence beginning with 2 protons fusing together, then building up, step by step, to helium, with energy shed at each stage. For working this out, Bethe would eventually receive a Nobel Prize, and there is a story, perhaps embroidered in the retelling, that on the evening he completed the calculation he walked out under the night sky with his companion, who remarked how beautiful the stars were, and he replied that at that moment he was the only person alive who knew what made them shine. True or not, the story captures something real. For the first time, the light of every star in the sky had an explanation written in the language of the nucleus. Bethe found, too, that nature runs the reaction by more than one route. In stars hotter and heavier than the sun, a different sequence takes over, one in which carbon and nitrogen act as go-betweens, ferrying protons together and emerging unchanged at the end. Like patient workers who assemble a product without ever being consumed by it, the sun uses a little of this path, but relies mainly on the simpler, slower chain of protons joining directly, and it is that simpler chain whose first step holds the secret of the sun's longevity. And buried in Bethy's chain of reactions was the resolution to the puzzle this whole story began with: the reason the sun is so slow. The very first step, the fusing of two protons, is the bottleneck. Because to make those two protons stick, one of them must transform into a neutron in the same instant, and that transformation is governed by the weak nuclear force. The weak force earns its name. It acts so rarely that this opening reaction is, by an enormous margin, the slowest link in the whole chain. So reluctant is it that the reaction has never once been observed directly in any laboratory on Earth. It is simply too rare to catch, and its rate is known only through calculation. Yet it is this reluctance, and nothing else, that sets the pace of the Sunday. Because the first step is so slow, the sun consumes its hydrogen at a crawl, and a crawl stretched across a star's worth of fuel is what gives it a lifetime measured in billions of years. The hook on which this whole account hangs is now fully unwound. The sun shines steadily for 10,000 million years, rather than flaring out in an instant, precisely because the weakest force in nature stands guard at the door of fusion, letting the reaction through only a little at a time. There is a second slowness inside the sun worth pausing on, because it deepens the same lesson. The energy made in the core does not escape to the surface in anything like the 8 minutes it then takes to reach the Earth. It cannot travel in a straight line. The interior of the sun is so dense that a packet of energy released at the center is absorbed and re-emitted again and again, knocked in a random direction with each step, staggering outward through the crush of matter, like someone trying to cross a vast crowd by being jostled from shoulder to shoulder. By this stumbling path, the energy takes not minutes but many thousands of years to work its way from the core to the surface, where at last it breaks free as sunlight and crosses to us in a few minutes more. The warmth on your skin was made in the heart of the sun long before you were born, and spent most of the intervening time simply trying to get out. Even within a single star, slowness is layered upon slowness, each layer set by a definite physical rate. The lifetime fixed by all this is not the same for every star, and the difference is itself a clock worth reading. How long a star lives depends almost entirely on its mass, but not in the way one might guess. A more massive star has more fuel, yet it burns through that fuel far faster because its greater weight squeezes its core to higher temperatures and drives fusion at a furious pace. The most massive stars are so extravagant that they exhaust themselves in only a few million years, a cosmic eye blink. The Sun, a middling star, takes 10,000 million. And the smallest stars, the dim red dwarfs that make up the great majority of all the stars in the universe, are so frugal with their fuel, fusing it so gently that they can shine steadily for many trillions of years. The universe is not yet old enough for a single one of them to have run out. Every red dwarf that has ever ignited is still burning now, and will go on burning long after the sun itself has died. The same reaction, governed by the same weak force, gives a span of a few million years to one star and trillions to another, purely according to how hard gravity is squeezing the core. Which is the quiet thread connecting all of this back to where the whole sequence of cosmic clocks must truly begin. A star's life is set by fusion, and fusion is set by the weak force and the temperature of the core, and the temperature of the core is set by gravity, by how fiercely the star's own weight bears down on its center. But that raises a prior question, one we have so far simply assumed away. Before any star can burn at all, it has to come into being, and a star does not assemble itself in an instant either. It begins as a vast, cold, almost unimaginably thin cloud of gas drifting in the dark, and turning such a cloud into a star is a slow business in its own right, with its own clock, set once again by gravity. To understand why the universe takes so long to light its fires, we have to go back to the moment before the fire, to the patient, grinding work of gravity pulling a diffuse cloud together against everything that resists it. Gravity has a strange reputation. We think of it as the force that pins us to the ground and hurls planets around the sun, something powerful and immediate. But measured against the other forces of nature, gravity is astonishingly feeble, by an enormous margin, the weakest of them all. The reason it seems to dominate the cosmos is not strength but persistence. Every other force can cancel itself out. Positive charge balances negative, and the pushes and pulls inside ordinary matter very nearly sum to nothing. Gravity never cancels. It only ever adds. Every scrap of matter pulls on every other, always inward, never opposing, and across the immense quantities of matter in a cloud or a galaxy, those countless tiny pulls accumulate into something that shapes the universe. Gravity is the architect of all large structure not because it is forceful but because it is relentless, and relentlessness, given enough matter and enough time, is its own kind of power. What it is not is fast. To see how slowly gravity actually works on the raw material of stars, you have to know how thin that material is. The clouds from which stars form are not the dense, billowing things the word suggests. They are vast, cold regions of gas, mostly hydrogen, so rarefied that a cubic centimeter might hold only a few hundred or a few thousand atoms, a far better vacuum than anything we can manufacture in a laboratory on Earth. They are cold almost beyond reckoning, a few degrees above the lowest temperature there is, and they sprawl across tens of light years. They contain enormous mass only because they are so staggeringly large. To turn a patch of such a cloud into a star is to compress it until its density climbs by something like 20 powers of 10, squeezing a wisp thinner than the emptiest vacuum into a ball of plasma, as dense as lead and far denser at its heart. Gravity can do this, but on diffuse gas its grip is so gentle that the falling together takes millions of years. There is a clean rule governing how long that collapse should take, and it depends on just one thing: the density of the gas. The thinner the cloud, the weaker gravity's pull on any given atom, and so the longer it takes everything to fall inward. A denser region collapses faster, a sparser one slower, and the relationship can be written down precisely. This is the freefall time, the most basic clock of star formation, and for the tenuous clouds drifting through a galaxy, it runs to millions of years, even in the simplest case, the case where nothing at all stands in gravity's way. But something always stands in the way, and the real story of why stars take so long to form is the story of those obstacles. The first is the gas's own warmth. As gravity squeezes a cloud, the gas heats up, and heat means pressure pushing outward, resisting the squeeze. A cloud can collapse only if its gravity is strong enough to overpower its own internal pressure, which is why the coldest clouds are the ones that form stars. Warmth fights collapse, cold permits it, and as the gas is compressed, it heats further, so to keep falling it must continually shed that heat, radiating it away into space as faint infrared light. The pace of collapse is throttled by how quickly the cloud can cool itself, a slow surrender of warmth that gravity must wait upon at every stage. The cooling is done by the cloud's own contents. Molecules and tiny grains of dust absorb the heat of compression and re-radiate it as faint infrared light that slips away into the dark. Without those molecules and that dust to carry the heat off, the gas would simply grow hotter as it squeezed, its rising pressure halting the collapse entirely. It is a quiet irony that a cloud can become a star only by continually giving away the very energy that gravity is pouring into it. The heat of falling must be shed almost as fast as it is made, or nothing falls at all. The second obstacle is spin. No cloud is ever perfectly still. Each carries some faint rotation, inherited from the swirling of the galaxy around it. And rotation has a stubborn property. As a spinning thing shrinks, it must spin faster, in the same way a turning skater speeds up by drawing in their arms. A cloud collapsing by 20 powers of 10 in size would, left to itself, spin up to such a furious rate that it would fling its own material outward and halt the collapse long before a star could form. For gravity to win, the cloud has to get rid of most of its spin, shedding it into surrounding material, into magnetic fields, threading the gas, and into the flattened, rotating disk that forms around the gathering core. This shedding of spin is one of the great bottlenecks of star formation, a problem nature solves only slowly and only partway. The disk itself is the visible signature of that compromise. Matter that could not fall straight in, because it was spinning too fast, settles instead into a broad rotating platter wheeling around the new star. Far from being wasted, that leftover spinning material becomes the stuff from which planets are later built. But that is a slow story for another stage, and it begins here, in the failure of a cloud to surrender its rotation all at once. And there is a third resistance, woven through the gas in the form of magnetic fields, which thread these clouds and brace them against their own weight, like an invisible scaffolding. The matter has to slip free of that magnetic support before it can fall, and it does so only by a gradual seepage that adds yet more time to the count. Between pressure, spin, and magnetism, a cloud that might in principle collapse in a few million years is held back, regulated, and slowed, so that the making of stars proceeds at a measured pace rather than all at once. It is worth noting, too, that across the very largest scales, the gravitational scaffolding of the cosmos is dominated not by ordinary matter at all, but by an unseen substance we detect only through its pull, the silent backbone on which the visible universe is hung. The outcome of all this resistance is that a great cloud rarely collapses into a single star. Instead, it fragments. As different regions reach the tipping point at slightly different times, the cloud breaks into many separate cores, each falling in on itself, so that a single vast cloud gives birth not to one star but to hundreds or thousands at once, a whole brood of suns emerging together over millions of years. Star formation is, in this sense, profoundly inefficient and profoundly unhurried. Only a small fraction of any cloud's gas ever ends up inside stars. The rest is heated, blown away, or left drifting, to be gathered again in some later age. Gravity assembles the universe's stars the way water carves a canyon, not in a rush, but by the patient accumulation of an unimaginable number of small, slow effects. None of this is mere theory. We can watch it in progress, because the sky is full of clouds caught at every stage of the work. In the great star-forming regions of our own galaxy, telescopes find dark, cold clouds with no stars in them yet. Alongside them, clouds with dense knots beginning to glow, and nearby, young stars freshly emerged, still wrapped in the tattered remains of the gas that made them, often still circled by the disks of leftover material. Because light from different distances shows us different ages, and because different clouds are at different points in their collapse, we can lay these scenes side by side and read the sequence, the way one might reconstruct a slow event from a scatter of photographs taken at unknown moments. The timescales that emerge from these observations confirm the calculation. Turning a cloud into a star is the work of millions of years, and the galaxy is always, everywhere, somewhere in the middle of doing it. This is the same gravitational clock, in the end, that we met inside the Sunday. There, gravity's inward squeeze set the temperature of the core, which set the rate of fusion, which set the lifetime of the star. Here, before the star exists, gravity's slow pull on diffuse gas sets how long it takes for a star to come into being at all. At every stage, from the thinnest cloud to the densest core to the fusing heart, it is gravity drawing matter together, and some opposing influence holding it back, and the balance between them that fixes the pace. Nothing collapses instantly, because nothing is ever entirely free to fall. But all of this, the cold clouds, the slow collapse, the patient fragmentation into stars, assumes something we have so far taken for granted. It assumes there is gas to collapse, neutral, coolable matter, spread thinly through a transparent space, across which its faint heat can escape. In the universe of today, that is simply the background condition, the stage on which everything happens. It was not always so. Wind the cosmos back far enough, and there were no clouds, no neutral gas, no transparent space for light to cross, only a smooth, glowing fog, so hot and so dense that matter could not gather, and light could not travel freely at all. Before gravity's slow hand could begin assembling anything, the universe itself had to change state. It had to expand, and cool, and at a particular moment turn from an opaque fire into the clear, dark, star-making space we now inhabit. That transformation, from opaque fire into clear and star-making space, ran on a clock of its own, the earliest of them all, the one from which every later slowness descends. To find the universe's earliest clock, we have to imagine a cosmos with no stars, no galaxies, no dark, transparent space at all, a universe that was, in its first stretch of existence, a single seamless glare. In those early times, everything that now floats as separate matter was crushed together into a searing plasma. Bare protons, helium nuclei, and a sea of loose electrons, all bathed in an overwhelming flood of light. It was hot beyond anything that exists today, and crucially it was opaque. Light could not travel across it. A photon setting out in any direction would almost instantly collide with one of the countless free electrons, and be flung off course, then collide again and again, so that light simply churned in place, trapped in the fog like sunlight lost inside a thick cloud. For its first hundreds of thousands of years, the universe glowed everywhere and yet was blind, a fire so dense it could not see itself. What changed this was nothing sudden. It was the slow, steady cooling that comes from expansion. Space itself was stretching, and as it stretched, the heat within it spread thinner and the temperature fell, degree by degree, across the ages. This is the cooling clock, and its pace was set by how fast the universe was expanding. For a long while, the cosmos remained far too hot for atoms to exist, Any electron that tried to settle onto a nucleus was immediately knocked loose again by the ferocious bath of light around it. The fog persisted not because atoms could not form, but because they could not stay formed. Only when the expansion had cooled everything to a particular threshold, around 3,000 degrees, reached when the universe was about 380,000 years old, did the light finally grow too feeble to tear atoms apart as fast as they assembled. At that moment, all across the cosmos at once, electrons settled onto nuclei and stayed there, and neutral atoms of hydrogen and helium came into being for the first time. The effect on light was instantaneous and total. With the free electrons suddenly bound up inside neutral atoms, there was almost nothing left to scatter the photons, and the fog lifted. Light that had been trapped and churning for hundreds of thousands of years could now stream freely in straight lines across newly transparent space, and most of it has been streaming ever since, uninterrupted, for the entire age of the universe. That moment of clearing is the oldest event we can directly see. Look far enough in any direction and you eventually reach it, a wall of light marking the instant the universe turned clear, beyond which no telescope can ever see, because before it there was only fog. That ancient light is still arriving today, and we have caught it. It was released as a warm glow, the color of a dull red heat, but in the billions of years since, the same expansion that cooled the early cosmos has stretched the light, along with everything else, drawing its waves out 1,000-fold until they are no longer visible at all, but have become faint microwaves, the gentlest whisper of radiation filling all of space. We call it the cosmic microwave background, and it is the single most important piece of evidence we have about the early universe, a direct photograph of the cosmos as it was at 380,000 years old, taken by light that left the scene then and is only now reaching our instruments. Its discovery, fittingly for this story, came by accident and was nearly missed. In 1965, two physicists at a laboratory in New Jersey, Arno Penzias and Robert Wilson, were testing an extremely sensitive antenna and kept finding a faint hum of noise they could not get rid of. It came from every direction in the sky, day and night, season after season. They checked every possible source, even evicting a pair of pigeons that had nested in the antenna and scrubbing out what the birds had left behind, and still the hum remained. What they had stumbled upon, it turned out, was the afterglow of the early universe itself, the cooled, stretched remnant of that first clearing light. Only a short distance away, a group of physicists had worked out that exactly such a glow should exist and were preparing to look for it. Penzias and Wilson had found it first, without meaning to, and the discovery confirmed that the cosmos had a hot, dense beginning and had been cooling and clearing ever since. In truth, the glow had been foreseen years before anyone detected it. Back in the late 1940s, a small group of physicists, reasoning about a hot early universe, had predicted that such an afterglow should still be detectable. Cooled by expansion to just a few degrees above the coldest temperature there is, a remarkably close guess at what Penzias and Wilson would stumble upon more than 15 years later. The prediction had simply been forgotten, or thought untestable, until the accidental discovery brought it roaring back. And once cosmologists understood what they were looking at, the faint hum became the most powerful instrument they had ever possessed. By measuring its temperature across the whole sky with ever greater precision, from balloons, from mountaintops, and from a succession of dedicated satellites, they could read off the age of the universe, the proportions of its basic ingredients, and the geometry of space itself. A noise that two engineers had tried for months to eliminate turned out to carry the most detailed record of the early cosmos in existence. When we map this ancient light with care, we find it astonishingly smooth, very nearly the same temperature in every direction, the mark of a young universe that was remarkably uniform, but not perfectly so. Printed faintly across it are ripples, regions very slightly warmer or cooler than their surroundings, differing by only about 1 part in 100,000. These almost imperceptible variations are among the most consequential things in all of cosmology, because they are the seeds of everything. Where the early universe was a touch denser than average, gravity had a little more to grip. Where it was a touch thinner, a little less. Every galaxy, every star, every planet that would ever form was written, in faint outline, into those tiny unevennesses in the infant cosmos. The whole structured universe grew from differences of 1 part in 100,000, but it grew slowly. And here the story returns to the patient theme that runs through all of it. After the fog lifted, the universe did not burst into stars. It entered a long, dark, silent interval that astronomers call the cosmic dark ages, a span of hundreds of millions of years in which there were no stars at all, only the cooling neutral gas spread almost evenly through an expanding, lightless space. The faint seeds were there, but they were only seeds, overdensities of 0.01%, and gravity had to work on them for an enormous stretch of time before they amounted to anything. This is the slowest kind of beginning imaginable, a runaway that starts from almost perfect flatness. In the denser regions, gravity pulled in a little more matter, which deepened the density, which pulled in a little more still, the advantage compounding over the ages the way a tiny lead can slowly widen. But compounding from 1 part in 100,000 takes time on a cosmic scale. For hundreds of millions of years, the universe simply darkened and drifted, its faint lumps very gradually gathering themselves, with no light anywhere to mark the slow work going on. Had any eye existed to witness it, there would have been nothing to see, no glow on any horizon, no point of light in any direction, only a cooling gas thinning and clumping in a darkness without stars. The only change was the imperceptible deepening of the densest regions, a gathering so gradual that across a human lifetime it would have shown no sign of happening at all. It is worth holding the strangeness of this in mind. There was an era, longer than the entire age of the Earth, during which the universe contained all the matter it has now, was already expanding and cooling on the schedule it still follows, and yet held not a single star. The cosmos was complete in its ingredients, and empty of fire. Everything was in place for stars to form, and nothing had formed, because the one thing the early universe could not be given was a shortcut. Gravity had to amplify those minuscule seeds across hundreds of millions of years, at the pace its own weakness allowed, until somewhere a clump of gas finally grew dense enough and cold enough to collapse on itself in earnest. And when at last that happened, the Dark Ages ended, not gradually but in scattered points of sudden brilliance, as the first stars in the history of the universe caught fire. They were the first objects ever to shine, the first light not left over from the beginning but newly made, and they brought the long darkness to a close. Yet these first stars were not like the sun, nor like any star that burns today. The gas they formed from was almost pure hydrogen and helium, untouched by any earlier generation, with none of the dust and heavier molecules that allow modern clouds to cool and collapse with relative ease. Forming a star from such pristine, stubborn material was a different and harder process, and it produced stars on a scale the universe has never quite matched since, giants whose brief, brilliant lives would begin the long transformation of a simple cosmos into a complicated one. The first stars faced a problem that no star since has had to overcome. The gas they formed from was almost perfectly pure, hydrogen and helium, and very little else, the raw output of the universe's own beginning. And pure hydrogen and helium are, awkwardly, very poor at getting rid of heat. A modern cloud cools itself easily because it is salted with carbon, oxygen, and grains of dust, all of which are superb at absorbing the heat of compression and radiating it away, letting the gas grow cold and fall together. The primordial gas had none of these. It had only the feeble cooling that hydrogen can manage on its own, and so as gravity squeezed an early clump and the gas heated up, there was almost no way for it to shed that heat. The rising pressure pushed back hard, and the collapse stalled unless the clump was very massive indeed. The consequence was that the first stars could not form small. A clump of pristine gas had to gather an enormous amount of material before gravity could overpower its stubborn warmth. And so the stars that finally lit up were giants, far more massive than the sun, perhaps tens or even hundreds of times its mass. They were the largest stars the universe has ever routinely made, and they shone with a fierce blue-white brilliance, flooding the dark cosmos with the first starlight it had ever known. After hundreds of millions of years of darkness, the universe finally had light it had made for itself. But here the clocks pull in opposite directions, and the contrast is striking. It had taken the cosmos an immense span, those long dark ages, to assemble the conditions for even one of these stars, gravity grinding away at faint seeds across hundreds of millions of years. Yet once a giant star ignited, it lived almost no time at all. Recall that the most massive stars burn through their fuel the fastest, squeezed by their own great weight to furious central temperatures, racing through in a few million years what the sun takes 10,000 million to accomplish. So the first stars were a paradox of pace, agonizingly slow to arrive, and then gone almost as soon as they came, blazing for a cosmic instant before exhausting themselves. The universe had waited hundreds of millions of years for a light that would last only a few million more. And yet those few million years changed everything, because of what the first stars did while they burned. Until that moment, the cosmos was chemically almost empty. The Big Bang itself had manufactured only the three lightest elements: hydrogen, helium, and a faint trace of lithium, and nothing more. It is worth pausing on why the Big Bang stopped there, because it is one of the rare moments in this whole account where a cosmic clock ran fast rather than slow, and the speed is precisely the point. In the first few minutes of the universe, everything was hot enough and dense enough for fusion to proceed everywhere at once, and in that brief window, protons and neutrons were welded together into helium on a furious schedule. But the same expansion that cools the cosmos was already at work, thinning and chilling the fire, and within only a handful of minutes the whole universe had dropped below the temperature at which fusion could continue. The door slammed shut almost as soon as it had opened. There was simply no time to build anything heavier than the lightest few elements before the conditions for fusion vanished from the cosmos entirely. That fleeting early furnace is why the universe began so barren, and why the long, slow work of making everything else fell to the stars, which alone could hold fusion going steadily for the billions of years that the manufacture of complexity would require. The brevity of the one fast clock guaranteed the length of all the slow ones. There was no carbon anywhere, no oxygen, no nitrogen, no iron. None of the substances from which planets and living things are built existed at all. Every one of those elements had to be made, and the only place to make them was inside stars. In the cores of the first giants, fusion did not stop at helium. It pressed on, building helium into carbon, carbon into oxygen, and onward up the ladder of the elements, forging in a few million years the heavier atoms the early universe entirely lacked. One of those steps deserves particular notice, because it is yet another reluctant, slow reaction of exactly the kind this whole story keeps returning to. To build carbon, a star must bring three helium nuclei together almost simultaneously, since there is no stable resting point with two. Three-body encounters are rare, and the reaction should by rights be far too slow to make any appreciable carbon at all. The astronomer Fred Hoyle realized in the 1950s that the universe is nonetheless full of carbon. We are full of carbon, and reasoned that there must therefore be some special feature of the carbon nucleus, a resonance, that makes the otherwise improbable reaction proceed efficiently enough to matter. He predicted the precise property the nucleus must have, on the grounds that without it neither carbon nor we could exist, and when experimenters went to look, they found exactly the feature he had foretold. It was a stunning piece of reasoning, and it sat at the heart of a larger achievement. Hoyle and his collaborators worked out, in detail, how stars build nearly all the elements heavier than helium, mapping the slow stellar alchemy that turns a simple cosmos into a richly stocked one. When the first giants reached the end of their brief lives, they returned their newly forged elements to the space around them, scattering carbon and oxygen and the rest back into the surrounding gas. That gas, no longer pristine, was now faintly enriched, and enrichment, it turned out, was self-reinforcing in the gentlest possible way. The traces of carbon and oxygen, the first stars left behind, were precisely the substances that gas needs in order to cool efficiently. So the next clouds to gather could shed their heat a little more easily, collapse a little more readily, and fragment into smaller pieces, producing stars less monstrous than the first. Those stars enriched the gas further still, and the generation after them could form smaller and more freely again. Step by step, over many cycles of birth and death, the universe was bootstrapping itself out of its original simplicity, each generation of stars making the next generation easier to form and richer in the ingredients of complexity. This is one of the most important and least hurried clocks in the whole of cosmic history, because it is the clock that eventually made us possible. A star like the Sun, modest in size and steady in its burning, could not have formed in the early universe at all. The gas was too pristine, too poor at cooling, to collapse into anything so small. Worlds of rock and iron and water could not have formed either, for the simple reason that rock and iron and water did not yet exist as elements in any quantity. Both the Sun and the Earth had to wait until enough generations of earlier stars had lived and died to seed the gas with the heavier atoms they are built from. We are, quite literally, made of the ash of stars that died before the Sun was born, the carbon in every cell, the oxygen in every breath, the calcium in every bone, the iron in every drop of blood, all of it manufactured in stellar cores and scattered across space across billions of years before any of it gathered into a planet, let alone a person. That is why the complexity of the present universe could not have been rushed. It is not merely that the early cosmos was simple and the later cosmos is intricate. It is that the intricacy had to be physically manufactured, atom by atom, in the cores of countless stars, and then patiently gathered and regathered through generation after generation. Each cycle took millions to billions of years, and there was no way to run them in parallel any faster, because each generation depended on the leavings of the one before. The universe is complicated today only because it spent billions of years slowly making itself so, with no shortcut available and none taken. For a long time, this earliest era was beyond all hope of seeing, reconstructed only from theory and from the chemistry of later stars. That is beginning to change. The light from the first stars and the first galaxies, set out more than 13 billion years ago, is among the faintest and most stretched out in all the sky, its waves drawn so far by the expansion of the cosmos that it now arrives as infrared, invisible to the eye. Only the most powerful telescopes, built expressly to gather that ancient infrared glow, can reach back far enough to catch it. When they do, they find the young universe already stirring with light, surprisingly early and surprisingly brightly, the first structures switching on closer to the dawn of time than some models had expected. We are, in effect, only now receiving the opening images of the cosmos's first morning, and reading in them the moment the long dark ages ended and the slow making of complexity began. The first stars, then, did not shine alone for long, and they did not shine in isolation. Even as they lived and died and seeded the gas, gravity was at work on a far larger scale, drawing the scattered clumps of early matter together into greater and greater concentrations. The points of first light were not spread evenly through the cosmos. They clustered, gathered by the same compounding pull that had assembled them into vast rotating islands of stars and gas. These were the first galaxies, and they too were built slowly, over hundreds of millions of years, turning so ponderously that even now, in the mature universe, a single one of their great rotations takes longer than the entire span since complex life first stirred on the Earth. For most of human history, no one suspected that galaxies existed at all. The faint spiral smudges scattered among the stars were thought to be clouds of gas within our own Milky Way, minor features of the one great system that was assumed to be the whole universe. The question of what they really were came to a head in the 1920s, and it was settled by Edwin Hubble, working with the largest telescope of the day. Hubble managed to pick out, within the great spiral of Andromeda, a particular kind of pulsing star whose true brightness can be deduced from the rhythm of its pulsing. And once you know how bright a star truly is, comparing that to how bright it appears tells you how far away it must be. The distance Hubble found was staggering. Andromeda was not a cloud inside our galaxy. It lay far beyond it, a separate island of stars, a galaxy in its own right, so remote that its light had been traveling toward us for an almost unimaginable time. At a stroke, the universe became vastly larger than anyone had pictured, a cosmos not of one galaxy, but of countless billions, each a great congregation of stars adrift in the dark. That sheer size is the first thing to grasp about galaxies, because it is the root of their slowness. A galaxy like our own spans 100,000 light-years, which is to say that light itself, the fastest thing there is, needs 100,000 years merely to cross it. Within that enormous span, hundreds of billions of stars orbit a common center, held in their great circling paths by the combined gravity of everything within. The stars are not still. They move at tremendous speeds by any human measure. Our own sun is sweeping around the center of the Milky Way at something like 230 kilometers every second. And yet the galaxy is so immense that even at that pace, a single circuit takes the sun roughly 250 million years. We can actually measure this turning, slow as it is, by reading the light of a galaxy carefully. As a galaxy rotates, the side spinning toward us has its light shifted very slightly toward the blue, and the side spinning away has its light shifted toward the red, the same effect that raises and lowers the pitch of a passing siren. From the size of that shift, astronomers can calculate how fast a galaxy turns, and the answer, time and again, is the same. Motion that is genuinely swift, played out across distances so enormous that a full rotation consumes hundreds of millions of years. Sit with that figure for a moment, because it is one of the most humbling clocks in the cosmos. The sun has been orbiting the center of the galaxy ever since it formed, 4.5 billion years ago, and in all that time it has completed only about 20 laps. The last time the sun occupied the position it holds now, the earliest dinosaurs were just appearing on the Earth. 2 laps ago, the most complex life on the planet was still confined to the sea. The galaxy turns so slowly that a single one of its rotations is long enough to contain the entire rise and fall of whole epochs of life on a world like ours. Nothing about this is unusual. It is simply what it means to orbit at the scale of a galaxy, where the distances are so vast that even great speed amounts to a stately, almost imperceptible wheeling. The galaxies themselves were not born whole. Like everything else in this account, they were assembled gradually, and from the bottom up. The faint seeds left in the early universe first gave rise to small clumps of stars and gas, and gravity, relentless as ever, drew these small systems toward one another over hundreds of millions of years. They met, merged, and combined into larger systems, which merged again into larger ones still, the great galaxies of today growing piece by piece from the gathering of smaller predecessors across billions of years. Our own Milky Way carries the evidence of this history within it. Streams of stars that were once separate small galaxies, swallowed and torn apart and woven into the larger whole, their remnants still traceable as faint threads looping through the galaxy's outskirts. A galaxy is not a thing that was made. It is a thing that is still being made, slowly, by the accumulation and digestion of its neighbors. We can watch this happening across the sky, frozen at every stage by the look-back effect. Here a pair of galaxies lean toward one another, their outer stars drawn into long, luminous bridges and tails. Their two disks are caught mid-collision, distorted into rings and plumes. Elsewhere, a great elliptical galaxy sits placid, the smoothed-out result of mergers long since completed. Because each scene is a different distance away, and a different age, we can arrange them into a sequence, and read the slow choreography of galactic collision, an event that for any single pair takes hundreds of millions of years to play out. Our own galaxy has such a collision in its future. The great spiral of Andromeda, whose distance Hubble first measured, is drawing toward us, and in something like 4 billion years the two will meet, and, over a further long stretch of time, merge into a single larger galaxy. Yet there is nothing violent about it on any human timescale. The stars within each galaxy are so widely spaced that almost none will actually strike another. The two great systems will instead pass through and around each other in a gravitational embrace lasting far longer than the present age of the Earth, slowly settling, over billions of years, into one. The most striking feature of a galaxy like ours, its graceful spiral arms, presents a puzzle that took a long time to solve and that turns, once again, on the slowness of galactic motion. The obvious assumption is that the arms are solid structures, great trailing limbs of stars sweeping around with the galaxy. But that cannot be right, and the reason is the very rotation we have been describing. The inner parts of a galaxy orbit faster than the outer parts, completing their circuits in less time. If the spiral arms were fixed ribbons of material, this difference in pace would wind them up tighter and tighter with every rotation, until after only a handful of turns, they would be coiled into an indistinct blur. Since galaxies have rotated dozens of times since they formed and still display clean, open spirals, the arms cannot be solid objects being carried around. They must be something else. The resolution, worked out in the 1960s, is that the spiral arms are not made of fixed material at all. They are waves, patterns of slightly greater density that move through the galaxy at their own pace, distinct from the orbiting of the individual stars. A star, on its long journey around the galaxy, drifts into an arm, lingers in the crowd a while as it passes through the denser region, and then drifts out the other side, much as a car moves through a slow patch of traffic without the traffic jam itself moving anywhere fast. The arm persists as a feature, even though the particular stars composing it are always changing. In the same way, a traffic jam can hold its place on a motorway for hours, while individual cars enter it and leave. The pattern endures, the contents flow through. And because the arms are regions where gas is squeezed to higher density as it passes through, they are exactly the places where new stars are most readily born, which is why spiral arms are picked out in the brilliant blue light of young stars and the glowing clouds of star formation. So a galaxy is not the static pinwheel it appears in a photograph. It is a vast, slow churning, in which stars circle on quarter-billion-year orbits, density waves drift through at their own measured pace, and the whole structure grows and reshapes itself over billions of years through the gathering of smaller systems. Every part of it is in motion, and every part of it is slow, because the scales involved are so enormous that even violent speeds are tamed into something that looks, from any single human vantage, like perfect stillness. A galaxy seen tonight and a galaxy seen 1,000 years hence would be, to all appearances, identical, and yet nothing in it is at rest. It is within this grand, slow wheeling that the smaller stories of the cosmos continue to unfold. In the spiral arms, where the density waves pile up the gas, fresh clouds collapse and new stars ignite, just as they have throughout the galaxy's history, the same slow gravitational gathering we traced earlier, still going on, arm after arm, across the turning disk. And around many of those new stars, something further begins, something that will take its own long span to complete. The same leftover material that could not fall straight into a forming star, the spinning disk of gas and dust we met before, becomes the workshop in which planets are assembled. That assembly is among the most patient processes in all of nature, building worlds not in great dramatic strokes but grain by grain, collision by collision, across millions of years, and it is this slow assembly that built the ground beneath our feet. The idea that planets are born from a disk of material around a young star is surprisingly old. In the 18th century, first the philosopher Immanuel Kant, and then the mathematician Pierre-Simon Laplace, independently proposed that the sun and its planets had condensed together out of a great rotating cloud, the planets forming from a flattened skirt of leftover matter spinning around the newborn star. They had no way to prove it, but the core of their picture has survived every test since. When a star forms, it does not consume all the material that falls toward it. The portion spinning too fast to fall straight in settles into a broad, flat disk of gas and dust wheeling around the new star, and it is from this disk, not from the star itself, that planets are slowly assembled. The word slowly is the heart of the matter, because the building of a planet begins at an almost absurdly small scale. The solid component of the disk starts as dust, individual grains, each a fraction of the width of a hair, drifting through the gas. These grains are the only raw material there is, and a planet must somehow be built from them. The first step is the gentlest imaginable. Grains drift into one another at low speeds and stick, held together at first by nothing more than the faint electrical attraction that makes dust cling to a surface. Two grains become a clump. Clumps collide and grow into flecks. Flecks gather into grains the size of sand, then grit, then small pebbles. Every step is a matter of soft collisions and chance encounters, repeated across the vast volume of the disk, for an immense number of cycles. It is worth holding in mind just how vast the journey is that this represents. To build a planet from a grain of dust is to increase a single object's mass by something like 40 powers of 10, a span so enormous that no single mechanism could possibly carry matter across all of it. That is precisely why planet building proceeds in distinct stages, each governed by a different process. Gentle electrical sticking at the smallest scales, then a troublesome middle realm where growth nearly stalls, then the takeover of gravity once bodies are large enough to pull on one another. Nature does not assemble a world in one motion. It hands the growing material from one mechanism to the next, like a relay run across 40 orders of magnitude, and each handoff takes its own time. This building by sticking does not proceed smoothly all the way up, and one stage in particular is so troublesome that it has a name among the scientists who study it. When the growing bodies reach somewhere around a meter across, they hit a barrier. Objects of that size, colliding, tend no longer to stick, but to bounce apart, or to shatter one another back into fragments. Worse, a body of about that size feels a persistent headwind from the gas of the disk, which is orbiting slightly more slowly than a solid object would, and that headwind drags on it, causing it to spiral inward toward the star and threatening to swallow it before it can grow any larger. For a planet to form at all, matter has to find a way across this barrier, most likely by gathering pebbles into vast loose swarms dense enough for their own gravity to pull them together into a solid body in one collapse, leaping over the troublesome size in a single bound. Exactly how nature manages this is still being worked out, but manage it does, and the result is a population of solid bodies a few kilometers across, large enough that gravity, at last, can take over the work. Once bodies reach that size, the pace of growth changes character. A kilometer-sized object has enough gravity of its own to reach out and pull in its neighbors, and the largest bodies, having the strongest pull, grow fastest of all, sweeping up the smaller debris around them. A few dozen dominant bodies emerge, each clearing its own zone of the disk, growing into planetary embryos the size of moons or small planets. And then the final stage is the most violent, and the slowest of all. These embryos, on crossing orbits, collide with one another in titanic impacts, merging in catastrophic mergers that take place over tens of millions of years, until, at last, a handful of full-grown planets remain, each having swept its region clean. The calm, ordered solar system we know is the survivor of a long demolition, the quiet end state of a process that began with specks of dust and passed through an era of world-shattering collisions. Through all of this, the star at the center is not a passive bystander. It sets the rules of where different kinds of planet can form. Through its heat, close to the star, the disk is warm enough that only rock and metal can condense into solids. Any water or other volatile substance there stays a vapor and is eventually driven off. Farther out, beyond a boundary astronomers call the snow line, the disk is cold enough for ice to freeze solid, which suddenly multiplies the amount of solid material available to build with. This is why the architecture of our solar system is arranged the way it is. Small, dense worlds of rock and metal close to the sun, and giant planets, which could gather far more material beyond the snow line, orbiting in the cold outer reaches. The same star that lights the disk also disciplines it, drawing an invisible line between the realm of rocky worlds and the realm of giants. And there is a deadline hanging over the whole enterprise, which is why even this patient process cannot be infinitely slow. The gas of the disk does not last. Within a few million years of the star's birth, its light and wind blow the gas away, and the disk thins and disperses. Any planet that needs gas, the great gas giants especially, must gather it before that window closes, which means the cores of the giant planets have to grow within just a few million years, a genuine race against the clearing of the disk. The rocky planets, which are built from solids rather than gas, can take longer, finishing their slow accumulation of embryos and giant impacts over tens of millions of years after the gas is gone. Either way, the building of a planetary system is bounded at one end by a deadline and stretched at the other by the sheer slowness of accumulation, and the whole affair, from first sticking dust to finished worlds, occupies many millions of years. We are no longer guessing at any of this. With modern telescopes, we can look directly at the disks around young stars and see the process underway. The sharpest images reveal these disks marked with concentric bright rings and dark gaps. The gaps apparently swept clean by planets in the act of forming, gathering the material along their orbits exactly as the theory says they should. Around one young star after another, we catch the building of worlds at different stages. Some disks still smooth and full, others already carved into rings by unseen growing planets. And closer to home, we hold actual pieces of our own solar system's construction in our hands. The meteorites whose ages pin down the birth of the solar system are themselves leftover fragments from this era, planetesimals that never grew into planets, preserved unchanged for 4.5 billion years, time capsules from the age of building. When we read their clocks, we are reading the construction date of the worlds. There is a lesson in the planet-building process that echoes everything we have seen. A world is not poured into existence ready-made. It is accumulated, particle by particle and body by body, through an unbroken chain of small events, no one of which could be skipped or hurried. The dust must stick before the pebbles can gather. The pebbles must collapse before the planetesimals can grow. The planetesimals must merge before the embryos can collide, and the embryos must collide before a planet can stand finished. Each stage waits upon the one before it, and each takes as long as its own physics demands. The slowness of planet formation is not an accident or an inefficiency. It is the simple consequence of building something enormous out of something tiny, with only the actual forces of nature to do the work, and no power to run them faster than they run. Our own planet was assembled in just this way, in the warm inner region of the disk around the newborn sun, out of rock and metal, across tens of millions of years of accumulation and collision. By the time it was finished, it had swept up enough material to become the largest of the rocky worlds, and the last great impact it suffered, a collision with another body nearly the size of a planet, flung enough debris into orbit to form the moon. But the Earth that emerged from all this was nothing like the world we live on now. It was a sphere of molten and half-molten rock, scorched by impacts, wrapped in a choking atmosphere, with no oceans, no breathable air, no solid stable ground, and certainly nothing alive. Building the planet had taken tens of millions of years. Turning that glowing, violent newborn into a calm blue world fit for life would take vastly longer still, and it would be governed, like everything else, by its own unhurried clocks. The newborn Earth was a world in name only. It had the right mass and the right orbit, but its surface was an ocean of molten rock, glowing dull red, churned by the heat of its own formation and by the relentless impacts of debris still raining down from the half-built solar system. There was no solid ground to stand on, no air anyone could breathe, no liquid water anywhere, only heat and motion, and the long, slow business of cooling that lay ahead. Everything that would make this planet habitable had still to happen, and each step had its own pace. The first great change came from gravity, sorting the molten planet by weight. In a body that is fully or partly liquid, the heaviest materials sink and the lightest rise, and the Earth contained a great deal of iron, dense and eager to fall. Across this early molten phase, the iron drained downward through the lighter rock and gathered at the center, forming the planet's metallic core, while the lighter silicate rock floated above it to become the mantle and, eventually, the thin crust. This sorting released yet more heat as the heavy metal fell, keeping the young planet molten longer, but it gave the Earth the layered structure it still has, a dense iron heart wrapped in rock, and that structure turned out to matter enormously for what came later. It mattered because the iron core, still liquid in its outer part and stirred by the planet's heat, began to act as an engine. The slow churning of that vast mass of molten metal generates the Earth's magnetic field, an invisible shield that reaches out beyond the surface and wraps the whole planet. Without it, the stream of charged particles flowing constantly from the sun would gradually strip away the upper atmosphere and erode the planet's store of water into space, as appears to have happened to at least one of our neighboring worlds. The Earth's slow internal engine has kept that shield switched on for billions of years, and it is one of the quiet reasons the planet held on to the air and water that life would need. A consequence of the sorting that happened in the first molten age protected the surface across all the ages that followed. The air and the oceans came next, and they came out of the rock itself. Trapped within the material that built the Earth were enormous quantities of gas and water, locked chemically into the minerals. As the interior churned and volcanoes broke the surface, these were released, outgassed, into the space above, building up the first real atmosphere, thick, hot, heavy with carbon dioxide and water vapor and nitrogen, but with no free oxygen at all, nothing a human could have breathed. Some of the water may also have arrived from outside, delivered by icy bodies wandering in from beyond the snow line, the cold region where water had frozen during the building of the solar system. However the water was sourced, it began as vapor, held aloft in a scalding sky above a surface, still too hot for it to settle. Then, as the bombardment slowly eased and the surface cooled, came the rain. When at last the Earth had shed enough heat for the temperature to fall below the boiling point of water, the vapor in that thick atmosphere could finally condense, and it fell, not as a passing shower but as a deluge that may have continued, in one form or another, across a very long span, draining the sky into the low places of the surface. The first oceans gathered in the basins of the cooling crust, and a world that had been all fire and rock became for the first time a world with seas. It is a transformation almost impossible to picture at full scale. An entire planet's worth of water, lifted into the sky as steam during the molten age, and then returned to the surface over ages of rain, filling the ocean basins drop by patient drop. We are not merely supposing all this. The Earth itself preserves witnesses to it, and they are among the most remarkable objects in geology. In the ancient rocks of Western Australia, geologists have recovered tiny crystals of a tough mineral called zircon, crystals so durable that they outlasted the very rocks that first contained them, surviving as the rocks around them were ground to sand and reformed again and again. The oldest of these grains, dated by the same patient uranium and lead clock that settled the age of the Earth, turn out to be about 4.4 billion years old, older than almost anything else on the planet's surface, formed within the first 150 million years of the Earth's existence, and the chemistry locked inside them carries a startling message. They appear to have formed in the presence of liquid water. The Earth, it seems, had cooled and gathered oceans far sooner than anyone once thought, not after a billion years of waiting, but within the first few 100 million, almost as soon as the bombardment allowed. This early water poses a puzzle that deepens the picture, and it leads straight back to the Sunday. A star like the Sun does not shine at a constant brightness across its whole life. As it slowly fuses hydrogen into helium, the composition of its core gradually changes, and over billions of years it brightens. The young Sun, 4 billion years ago, was therefore noticeably fainter than it is today, by perhaps a quarter or more. By the simplest reckoning, that dimmer sun should have left the early Earth frozen solid, its young oceans locked in ice. Yet the evidence says there was liquid water, and abundant. The resolution lies in the air. The early atmosphere, thick with carbon dioxide and other heat-trapping gases, held in far more of the sun's warmth than our atmosphere does now, keeping the surface temperate beneath a weaker Sunday. As the sun slowly brightened over the ages, the atmosphere slowly changed in concert, and the planet held, by a long and not fully understood balancing act, within the narrow range in which water stays liquid. Even the habitability of the Earth, it turns out, has been a slow negotiation between a gradually warming star and a gradually shifting sky. That bombardment, though, was not finished. For hundreds of millions of years after the planet had a crust and seas, the leftover debris of the solar system continued to fall, in a long, slowly declining rain of impacts, some of them large enough to vaporize oceans and resurface whole regions of the planet. A world can have water and still be no place for anything delicate to survive, repeatedly scoured by collisions on a scale that dwarfs anything in recorded history. Habitability was not a switch thrown once and for all. It was a condition the Earth grew into gradually, as the impacts thinned, the crust thickened and stabilized, and the wild swings of the early surface settled toward something steadier. There was no single morning on which the planet became safe. There was only a long, uneven easing, stretched across more time than complex life has since existed, during which the Earth slowly stopped being a place that destroyed things and started being a place that could keep them. There was even a stabilizer overhead. The Moon, flung off in that last great impact during the planet's assembly, settled into orbit and, over the long term, has helped to hold the Earth's spin axis steady. A planet's tilt can wander over time, and large wanderings would send the climate lurching between extremes. The steadying pull of a large moon has kept the Earth's tilt within a narrow range across the ages, smoothing the long-term climate in a way that favored the slow development of life. The violent collision that scarred the young Earth left behind, as a kind of compensation, a companion that would help keep the planet's weather within livable bounds for billions of years. Put all of this together, and a pattern emerges that we have seen at every scale. Making a habitable planet was not a single event, but a long sequence of slow ones. The molten sorting that built the core and lit the magnetic engine, the outgassing that raised an atmosphere, the cooling that allowed the rains that filled the seas, the slow fading of the bombardment, the gradual stabilizing of crust and climate. Each step depended on the ones before it, and each took its own span of time, so that the whole process of turning a glowing ball of impact-shocked rock into a stable blue world with oceans and a sheltering atmosphere unfolded across hundreds of millions of years. By the end of it, the Earth was, at last, a place where something could live. But a place where life could exist is not the same as a place where life does exist, and between those two states lies perhaps the deepest threshold in this entire story. The early Earth had oceans, an atmosphere, a steady flow of energy from the sun and from its own hot interior, and a rich chemistry of carbon and water, every ingredient, so far as we can tell, that living things are made from. What it did not yet have was life. How a world stocked with the right chemicals became a world inhabited by things that grow, copy themselves, and evolve, is a question we have not fully answered. But we do know one thing about it with confidence. Like everything else in the history of the cosmos, it did not happen quickly. The origin of life remains the great unsolved gap in this whole sequence. We can trace, in some detail, how the elements were forged, how the planet was built, how the oceans gathered, but the step from a sea of interesting chemistry to the first thing that could be called alive is one we cannot yet reconstruct. What we can do is read the clock that tells us when it happened, and the answer is surprising. Life did not keep the young Earth waiting. The oldest direct traces of it, layered mounds of rock called stromatolites, built up grain by mats of microbes in shallow water, go back at least 3.5 billion years, and fainter chemical hints of living processes reach back further still, close to the time the bombardment eased and the oceans settled. As best we can tell, life appeared within a few 100 million years of the Earth becoming able to support it, quickly, by the standards of this story. We are not wholly cut off from that distant microbial world, because in a few quiet corners of the planet it still persists. In certain shallow, salty bays, mats of microbes go on building the same layered stone mounds their ancestors built more than 3 billion years ago, trapping and binding sediment grain by grain, dome by dome, exactly as they did when these were the most advanced structures on Earth. To stand beside them is to stand beside a living fossil of the planet's youth, a working remnant of the long age when such mats were the whole of visible life. They are slow even now. A mound may take a human lifetime to grow the thickness of a hand, and that slowness is itself a faithful echo of the unhurried pace at which life first established itself on the young Earth. That early start makes the rest of the timeline all the more astonishing, because having arrived so promptly, life then spent an almost unimaginable stretch, going almost nowhere. For roughly the first 3 billion years of its existence, the great majority of the entire history of life on Earth, living things were nothing but single cells, microbes, and only microbes, for billions of years. There were no plants, no animals, nothing with a body, nothing you could see without a microscope, for a span of time longer than it had taken the sun to form, and the earth to cool, and the oceans to gather, several times over. The slowness, in the story of life, is not in its beginning. It is in the enormous patience of its middle. Part of what filled that long microbial age was a transformation of the whole planet, carried out by life itself, on a clock of staggering length. At some point, certain microbes evolved the ability to harness sunlight to make their food, and as a byproduct of that chemistry, they released oxygen, a gas that had been almost entirely absent from the Earth's air. One might expect the atmosphere to have filled with oxygen quickly once this began. It did not. For hundreds of millions of years, almost every scrap of oxygen the microbes produced was immediately consumed, soaked up by the vast quantities of dissolved iron in the early oceans, and by other hungry chemicals at the surface. The oxygen rusted the planet before it could ever fill the sky. Only after the oceans and rocks had been thoroughly oxidized, their iron turned, quite literally, to rust and laid down in great banded formations that still streak the ancient rock, could free oxygen finally begin to accumulate in the air around 2.5 billion years ago. The whole Earth had to be chemically saturated, like a sponge soaked to capacity, before the atmosphere could change. It is one of the slowest and most consequential clocks in the planet's history, a global transformation that took the better part of 1 billion years to complete, and that rewrote the conditions for everything that would live afterward. The change was not gentle for the life already present. To the microbes that had evolved in an oxygen-free world, the new gas was a poison, corrosive, and deadly, and its slow rise drove much of that older life into retreat, into the muds and depths where oxygen could not reach, where its descendants still hide today. Yet oxygen also opened a door that could not have been opened any other way. Drawing energy from food using oxygen yields far more power than the airless chemistries that came before, and that surplus of energy is precisely what complex, active, large-bodied life would later require to exist at all. The same slow poisoning of the planet that killed off so much of the old world laid down the energetic foundation for the new one. Nothing about it was quick, and nothing about it was kind. But without that billion-year rusting of the Earth, there could never have been a creature large enough or energetic enough to wonder about any of it. Even with an oxygen-rich atmosphere, complexity was in no hurry. The next great threshold, the leap from simple cells to complex ones, the kind with an enclosed nucleus and specialized internal machinery, the kind that all plants and animals are built from, took perhaps another billion years or more to arrive, and when it came, it seems to have come through a single extraordinary accident. One simple cell engulfed another and, instead of digesting it, kept it alive inside, the two settling into a partnership so successful that the captured cell became a permanent component of the larger one, its descendants powering complex cells to this day. The biologist Lynn Margulis spent years arguing, against widespread resistance, that this is how complex cells arose, by ancient mergers rather than by gradual modification, and the evidence eventually proved her right. But the point for our purposes is the timing. This merger, on which all visible life depends, appears to have happened only once, after life had already existed for some 2 billion years. It may have been one of the rarest and most difficult steps of all, a bottleneck the universe took an eternity to pass through. Only after that, only in roughly the last sixth of the history of life, did the familiar living world begin to take shape. Complex cells gathered into the first multicellular bodies. Those bodies diversified, slowly at first and then in a great flowering a little over 500 million years ago, into the ancestors of the animals and plants we know. Every creature you have ever seen, every forest and reef and swarm, belongs to that final, thin slice of time. The Earth has been alive for nearly 4 billion years, and for more than 3 of them, there was nothing on it more elaborate than a film of microbes on a wet surface. The lush, populated planet of today is a very late development indeed. There is a way of looking at all this that closes a circle opened long ago in this story. Recall the 19th century crisis, when Lord Kelvin's physics seemed to deny the Earth the immense ages that Darwin's theory of evolution demanded. Darwin needed deep time, hundreds of millions of years, at the very least, because natural selection works only by the slow accumulation of tiny inherited changes, generation upon generation, and great transformations cannot be rushed when each step is so small. Kelvin's verdict made that time seem unavailable, and it weighed on Darwin to the end of his life. But Darwin's instinct was right, and Kelvin's premise was wrong, and the very clock that overturned Kelvin, radioactivity, handed biology not just the hundreds of millions of years it had asked for, but billions. And when we read the record of life against that vast corrected timescale, we find that evolution used nearly all of it. Life did not race to complexity the moment it could. It crept there, across spans of time so enormous that even Darwin might have been surprised, held back at each great threshold until the slow machinery of variation and selection and the occasional fantastically improbable accident could carry it across. The deep time that Kelvin tried to deny is exactly the deep time the living world turns out to have needed. So life, too, runs on a clock, or rather on several. There is the chemical clock of the cell, the rate at which inherited information can vary and be tested and refined. There is the planetary clock of the great oxygenation, the slow saturating of a whole world's chemistry. And there are the rare, halting thresholds, the origin of life itself, the birth of the complex cell, each of which seems to have taken an age to cross. None of these could be hurried, because each depended on processes with their own fixed and unhurried rates. The speed of chemistry, the rate of mutation, the patient compounding of selection across countless generations. The richness of the living Earth is not a sudden gift. It is the slow output of billions of years of biological timekeeping. And all of this unfolded on a stage that was itself in constant, ponderous motion. While life crept from microbes toward complexity, the very surface beneath it was being remade. Continents drifting and colliding, mountains rising and wearing away, the crust endlessly recycled. The same deep time that the living world required is recorded, quite independently, in the rock itself, in processes so slow that to a human eye they seem like the very definition of permanence. The ground we call solid and unchanging is in fact one of the great clocks of the planet, and learning to read it was, once again, the work of patient detectives piecing together a story written in stone. The hardest clocks for a human being to read are the geological ones, because they run so slowly that within a single lifetime they appear not to run at all. A mountain looks eternal, a coastline looks fixed. The solid rock underfoot is our very image of permanence, the thing we mean when we call something stable. And yet the rock is one of the most active timekeepers on the planet, recording and driving change on a scale that simply outruns our senses. Learning to see that motion, and then to measure it, was one of the great intellectual achievements of the last few centuries, and it transformed how humanity understands its own place in time. The first person truly to grasp the immensity of geological time was an 18th century Scottish farmer and naturalist named James Hutton. Studying the rocks of his own country, Hutton saw things that demanded enormous spans of time to explain. He found places where layers of rock had been laid down flat under water, then tilted on end, then worn away, then buried again under fresh horizontal layers, a sequence of events, each slow in itself, stacked one upon another with vast gaps of lost time between them. At one celebrated spot on the Scottish coast, where ancient near-vertical rock is capped by younger horizontal beds, he understood that he was looking at the record of an almost unfathomable history, far longer than the few thousand years then commonly assumed. Surveying it, he famously concluded that he could find no vestige of a beginning and no prospect of an end, meaning not that the earth was truly eternal, but that its history reached back so unimaginably far that its origin lay entirely beyond what the rocks could show. He had discovered deep time by reading it directly from stone, long before anyone could put a number to it. The rock can be read this way because it is laid down in order. Sediments settle layer upon layer, the older always beneath the younger, so that a cliff face or a canyon wall becomes a stacked sequence of time, the deepest bands, the most ancient, each higher band a later age pressed down upon the last. Within those layers lie fossils, the remains of the creatures alive when each band was laid, changing from level to level as life itself changed, so that the strata record not only the passage of time, but the order of events within it. To walk down through a deep gorge is to walk backward through hundreds of millions of years, reading the planet's history in the wall, the way one might read the rings of an unimaginably old tree. The whole science of geology began with the realization that the rock is not a static thing but a written record, and that the writing is chronological. The numbers came much later, and they came from the same man who had given the Earth its age, Arthur Holmes. Holmes did not only use radioactivity to date the rocks, he also turned his mind to what drives the great geological changes Hutton had glimpsed, and he arrived, decades ahead of general acceptance, at very nearly the right answer. He proposed that the slow leak of heat from the Earth's radioactive interior stirs the deep rock into vast, creeping currents, that the mantle, though solid, flows over geological time like extraordinarily stiff treacle, and that these currents are powerful enough to drag the continents themselves across the face of the planet. It would be a generation before the full theory of drifting plates was confirmed and accepted, but Holmes had seen the heart of it. The Earth's surface is not fixed, but is carried about, very slowly, on the churning of its own hot interior. This is what we now call plate tectonics, and it is the master clock of the solid Earth. The outer shell of the planet is broken into great plates that move, driven by that deep, slow churning, at a pace of only a few centimeters a year, about as fast as your fingernails grow. It sounds like nothing, but sustained across millions of years, a few centimeters a year carries continents from one side of the globe to the other, opens and closes entire oceans, and drives land masses into one another, with enough force to crumple their edges skyward into mountain ranges. The greatest peaks on Earth are the slow-motion wreckage of continental collisions, rising a fraction of a millimeter a year as one plate grinds into another, built not by any sudden upheaval, but by the patient accumulation of an imperceptible motion across an immense span of time. And as fast as mountains rise, the weather tears them down, on a clock just as slow and just as relentless. Rain, frost, wind, and ice break the rock grain by grain. Rivers carry the grains to the sea, and over tens of millions of years even the mightiest range is worn to stumps. There are mountain belts on Earth today, low and rounded and ancient, that were once as high and jagged as any on the planet, since ground down by hundreds of millions of years of erosion. The rock is caught in an endless slow cycle, thrust up by the moving plates, worn away by the weather, washed into the oceans as sediment, buried and compressed into new rock, and eventually lifted and exposed to begin again. The ocean floor itself is perpetually recycled, created at great undersea ridges and swallowed back into the interior elsewhere, so that none of it is older than a small fraction of the planet's age, while the continents preserve far more ancient stone. The whole surface of the Earth is a single vast, achingly slow machine, turning rock over and over across hundreds of millions of years. All of it is driven, at bottom, by the same source we met when radioactivity first overturned Lord Kelvin. The heat slowly leaking from the Earth's interior, much of it generated by the decay of radioactive elements deep within. That heat stirs the mantle. The stirring moves the plates. The moving plates raise the mountains. The mountains feed the erosion. And the whole system grinds on at the stately pace that the slow creep of hot rock allows. Tectonics is unhurried for the same reason everything in this story is unhurried, because the process that powers it has a fixed and gentle rate, and there is no way to make solid rock flow any faster than its nature permits. When we lay our own history against this geological clock, the result is humbling, almost beyond expression. The rock record of the Earth is a stack of pages, billions of years deep. Recorded human history, every civilization, every written word, every event we have names and dates for, occupies the very thinnest skin at the top, a layer so slight it would be all but invisible in the column of the ages. The oldest structures human beings ever raised are a few thousand years old. In that same few thousand years, a tectonic plate has moved, perhaps the length of a few rooms, and a great mountain has lost a sliver of height too small to notice. Everything we tend to call ancient, the first cities, the first writing, the deepest reaches of human memory, is younger than the most recent flicker of the geological clock. We have built our entire story inside a single thin band near the top of the rock, and the rock beneath it goes down and down, recording age upon age in which nothing human existed at all. This is the lesson the slow clocks press upon us most forcefully. We are fast creatures, brief creatures, living at a tempo utterly unlike the tempo of the cosmos that made us. A human life is measured in decades. The processes that built the ground we stand on are measured in hundreds of millions of years. The star that warms us keeps time in billions. We are, in every direction, dwarfed by the spans involved. And yet, this is the strange and redeeming turn. We are the part of all this slowness that has learned to perceive it. The rock cannot read itself. The sun does not know its own age. It is we, the quickest and most fleeting things in the whole account, who have worked out the rates of all the rest and assembled them into a history reaching back to the beginning. There remains one clock larger than any we have yet read, the one that encompasses all the others. The clock of the universe itself, the great expansion that has been running since the beginning and that governs the entire future of the cosmos. To read it is to ask not only how the universe came to take so long over everything, but how much time it has left, and what becomes of all these patient processes in the end. And it returns us, at the last, to the most remarkable fact in the whole story, that on at least one small world, the universe has produced something able to look up, measure its slow heartbeat, and understand it. The largest clock of all governs the universe entire, and we came to read it in the same way we read so much else, through light. In the 1920s, building on the work of others who had measured the colors of distant galaxies, Edwin Hubble noticed something extraordinary about that light. The galaxies were almost all shifted toward the red end of the spectrum. Their light stretched to longer wavelengths, and the more distant the galaxy, the greater the stretch. There was only one good explanation. The galaxies were moving away from us, and the farther off they lay, the faster they were receding, not because we sit at any special center, but because space itself is expanding, swelling everywhere at once, carrying the galaxies apart, like marks drawn on the surface of a balloon being slowly blown up. The whole universe is growing. An expanding universe is also, when you run it backward, a universe with a beginning. If everything is flying apart now, then everything was closer together in the past, and closer still further back, until at some finite time ago, the whole cosmos was compressed into an unimaginably hot, dense state. The beginning we have been circling throughout this account. A Belgian priest and physicist, Georges Lemaitre, had in fact reasoned his way to an expanding universe from theory alone, a little before Hubble found it written in the light, and had grasped that it implied a cosmos that began from a single primordial state. The idea was not universally welcomed. Fred Hoyle, the same astronomer who later worked out how stars build the elements, disliked the notion of a sudden beginning and coined a mocking name for it, the Big Bang, which, to his lasting irritation, stuck and became the accepted term for the very theory he opposed. But the evidence only deepened. The receding galaxies, the afterglow of the early fire we met in the cosmic microwave background, the precise proportions of the lightest elements forged in the first minutes, all of it pointed the same way, to a universe that began hot and dense and has been expanding and cooling ever since. The rate of expansion, read from the receding galaxies, gives us the grandest clock there is, the age of the universe itself, which comes out to about 13.8 billion years. Every other clock we have read fits inside this one. The 10 billion year life of the sun, the 4.5 billion year age of the earth, the 3 billion year reign of the microbes, the hundreds of millions of years for a galaxy to turn, all of them are spans carved out of this single overarching duration, the time that has passed since space began to grow, and the expansion is not finished. As far as we can tell, it will never finish. If anything, it is quietly speeding up, the galaxies drifting apart a little faster as the ages pass. This lets us run the great clock forward as well as back, and read something of the universe's future, a future every bit as unhurried as its past. The stars will go on forming for a long while yet, but not forever, because the supply of fresh gas is finite and is slowly being locked away. In time, across hundreds of billions of years, star formation will dwindle and cease. The brightest, most massive stars will be long gone, and the universe will be left to the dim red dwarfs, those most frugal of stars we met before, which burn so slowly that they will go on shining for trillions of years after the last large star has died, outlasting the present age of the cosmos, 100 times over and more. The universe will grow gradually darker and redder and quieter, not with any drama, but with the same patience that has marked every age of its history. The quickening expansion adds a strange loneliness to that future. As space stretches ever faster, the distant galaxies are being carried away from us more and more quickly, and in the far future, they will recede so fast that their light can no longer cross the widening gulf to reach us at all. One by one, over billions of years, they will dim and slip beyond the horizon of the visible, until a future observer in our galaxy would see only an island of nearby stars adrift in an apparently empty dark, with no sign that the wider universe of galaxies had ever existed. We are, in a sense, living in a privileged moment for reading the cosmos, late enough that its history has unfolded and its light has had time to arrive, but early enough that the evidence has not yet been carried beyond reach. The clocks can still be read now. They will not always be so legible. Beyond even that lies a future so distant it strains the meaning of the word. Once the last stars have finally guttered out, the cosmos enters an age of cold and dark whose spans dwarf everything that came before, an emptiness measured not in billions of years but in numbers with dozens of zeros. And in that unfathomable future, even the most enduring objects in the universe slowly give way. The black holes, the longest-lived structures of all, themselves evaporate at last, leaking away over timescales so vast that a 1 followed by 100 zeros of years is needed merely to write them down. That is the slowest clock we know of, and it sets the faint final horizon of the cosmic story, slowness carried to its ultimate conclusion. Set against these spans, a human being is almost nothing. We have measured the universe's slow clocks and found, at every turn, that we are dwarfed by them, that our lives are shorter against the life of the sun than a single heartbeat is against the whole of human history, that our entire civilization is a film too thin to see on the face of the rock, that everything we have ever done occupies a sliver at the very end of a story 13 billion years long. By every measure of duration, we are the briefest things in the account. And yet here is the turn that this whole journey has been building toward. We are also the only part of that account known to have understood it. The sun has kept its 10 billion year time without any awareness of doing so. The rocks have recorded their hundreds of millions of years with no one to read them. The light from the early universe traveled for 13 billion years before it fell, at last, upon instruments built by a creature that could grasp what it meant. In little more than a single century, a span so short it would not register on any of the clocks we have discussed, a fast and fragile species worked out the rate of nearly every slow process in existence. We learned that light has a finite speed, and used it to look back in time. We found the incorruptible clock inside the atom, and read from it the true age of the earth. We discovered why the sun burns slowly, and traced the manufacture of the elements through generation after generation of stars. We measured the turning of galaxies, the building of worlds, the rise of oxygen, the drift of continents, and the expansion of the universe itself. The slowest timekeepers in creation were read and understood by the quickest minds within it. It was not the work of any one person, but of a long relay of them, each handing the problem on. Romer timing a moon to catch light in the act of traveling, Kelvin reading the wrong clock with magnificent rigor, Rutherford and Holmes finding the right one inside the atom, Eddington and Bethe explaining the fire of the stars, Hutton and Hubble grasping the depth of time and the growth of space. Across a few generations, a creature that lives for decades assembled the biography of a cosmos that has run for 13 billion years. This is what lies beneath the question we began with. The universe does not rush, and the reason was never patience, never some temperament of waiting written into the cosmos. The reason is physics. Every process that seems slow is slow, because a definite law fixes its rate. The weakness of the weak force that throttles the sun, the feeble, relentless pull of gravity on diffuse gas, the fixed speed of light, the unchangeable tick of radioactive decay, the gentle creep of hot rock, the steady stretching of space. None of these can be hurried, because each is set by the deep, unbending constants of nature, and the long unfolding of the universe is simply what those constants produce when they are left to run. The slowness is not a mood. It is a measurement, and we have learned to take it. If you enjoyed this exploration of the deep clocks that set the pace of the cosmos, a like or a subscribe helps us continue making them. So perhaps the truest picture of the universe is not the still, silent expanse it first appears to be on a clear night. It is a great assembly of clocks, nested one inside another, each ticking at its own appointed rate, the fast flicker of a fusing proton, the long burn of a star, the slow wheel of a galaxy, the immense creep of the expanding cosmos, and at the very far edge, the all but endless evaporation of a black hole. They run at every scale, from the fraction of a second to the one with 100 zeros, and together they keep the time of everything that has ever happened or will. We are the smallest and swiftest hands on that great dial, here for the briefest moment, and yet, somehow, we are the hands that learn to read the face. The universe still has plenty left to reveal, and we will be following it as it does.